Hi class, we are now on 18.6, precipitation. Remember, precipitation is an insoluble compound in a solution, and this is where you would check that, in Chem 111, you would have a solubility chart and you would see what would make an insoluble compound or precipitate and which would not. But we're going to be looking at Q, the reaction quotient against the KSP. So remember, the KSP is a measure of a compound's solubility. Q is the reaction quotient, and it came up in another chapter. It is a let's go make sure you understand. It is an ionic compound that dissolves is the product. So the product of the ionic compound dissolving, so ions. The concentration of the ionic compounds raised to their stoichiometric coefficients. Now the big difference between them is KSP is only at equilibrium, where Q, the conditions are any value. At any and under any conditions that you can determine Q. So for Q, you can have a measurement of the product of the ion concentrations at any under any condition, so any time on those. So let's make sure we understand Q and KSP against each other here. So here we have cadmium fluoride, and then it dissolves into cadmium ions and fluoride ions. And then we have our Q. So everything's set up as if it's an equilibrium constant. So if you look at Q is less than KSP, the solution, it's not saturated yet. That means that more of the ionic compound can be dissolved. What is saturated? Remember, we have this should have been covered in 110 and also I believe 111. There's saturated, unsaturated, and supersaturated. Saturated means that no more will dissolve. No more ions can go in and dissolve. Remember, you're dealing with a solid that needs to dissolve, but it gets to a point that it's so saturated there, it can't do it anymore. Unsaturated means it can still dissolve. It can still take on more ions. And supersaturated is this, it's a rare, very unstable, extremely unstable conditions where it has actually dissolved more than what it should, and it's at a breaking point that one little thing, even sometimes just slightly accidentally hitting the bottle, can cause it to come out. The precipitation will come out of it. So it's a really, really unstable point where it's still in solution. That's what supersaturated means. So here's a perfect example. Here is a precipitate. You see the precipitation happening. Here is a supersaturated. I've actually done this in class in another school. This is so saturated that it's complete. It needs one little thing to cause it to end up being like this. It crystallizes out. And that's a supersaturated. I mean, it's past the solubility. It's very unstable, and it actually wants to precipitate out. So all they do is add one crystal, and that's the one little thing, the domino, that pushes everything down. Okay, so let's do some problems to understand understanding Q and KSP. Equal volumes of a solution of 0.0015 molar. I apologize. Silver perchlorate and a solution of 0.0015 molar sodium chloride are mixed. Will silver chloride precipitate? Will this become a precipitate? So we have two different solutions of the same molarity. Both of them have the same molar volume. All right, so to calculate Q, we can determine KSP. KSP is given to us. We can always look that up. But what about Q? How do we determine where this is on the spectrum that we just looked at? So we calculate Q from the post-mixing conditions, which means they were added together, and compare it to the KSP. Now, based on that, we can then figure out, looking at this, where it is in the reaction. So we set it up. Here's Q. We set it up with the ions. Remember, we don't include solids. And then we take the molarity. Now, this is something they're not talking about. We take the molarity but divide it by 2 in this case, because I had it down here. Equal volumes of the solution have been combined, and the final solution concentrations are half their original. So they're not the strongest, they're not the same molarity, because they've been, in a sense, diluted. And that's because of that, because there's other solutions in there, the molarity is cut by half. So in this case, we take Q, we look at plugging in the molarities, plus the fact that they're diluted, so they're not that same molarity, and it equals 5.63 times 10 to the negative 7. So now we take this, we look at the KSP, and let's see, KSP has a smaller value than Q. That means that Q is greater than KSP. So what does that mean? If we go backwards, the solution is past the point of saturation, and the excess ionic compound will precipitate from solution. So it's saturated, and the rest of it is now going to precipitate out because it can't handle being in a soluble environment. So until it actually gets back to equilibrium, and then it'll stay at that. So that is one, why we divide by 2. And the second thing, and I took this right out of a book, so this is their sentence for this, because it is kind of weird that it's not discussed in this case. Okay, so selective precipitation. A solution containing several different cations. So what if we needed to actually remove some cations? So, you know, especially like hard water. If you want to remove the ions that are responsible for the hard water, you want to get rid of them, so that doesn't happen. So this is selective precipitation. What if we want to get rid of those but leave the rest of them? So we want to pull out some but leave the others. So a reagent, which is whatever we want to use that will react with it to get it into precipitation. And some of them, ideally, if you want to remove maybe 2 ions out of it, if you find a perfect reagent, that in some cases you can, that can remove both of those, and you can do that as long as that KSP value are really different from each other. So you could use it again. In cases where several ions are present in the solution, 1 or more ions can be selectively precipitated out, meaning removing one but leaving the rest, using a reagent based on the solubilities, different solubilities of the compound. So we're going to look at this. So for example, if you have a solution that contains silver and magnesium ions, the addition of acid, HCl or NaCl, selectively precipitates silver, since silver chloride has a KSP that's 1.77 times 10 to the negative 10, which has a much slower solubility than magnesium chloride, which basically what they're saying is that they didn't give the value for the other one, which doesn't make sense to me. But because it's the KSP has such a low, remember, the lower the value, the more insoluble it is. So it's going to, and the higher the value, the more soluble it is. So in this case, this is going to precipitate out once it starts getting to that low value. And magnesium chloride, it's going to before it even gets to the magnesium chloride. Okay, so a solution contains equal concentrations of barium, lead, and calcium ions. When potassium sulfate is added to the solution, which cation precipitates first? So what they want us to look at is the KSP values, because the KSP values are going to tell us which one of these will precipitate out first. So if we look at these, we have 1.07 times 10 to the negative 10. We have lead 2 sulfate, which is 1.82 times 10 to the negative 8. And we have 7.10 times 10 to the negative 5. B and C have larger values than A, which means they're more soluble. But B has a low value, so it's the least soluble. So because of that, it's the most insoluble. It will precipitate out first over the others. Suppose you have solution containing barium and magnesium ions. Which of these salts could you add to selectively precipitate barium? So let's take a look at these. So again, we're going to look at values, KSP values, so barium carbonate and magnesium carbonate, because we want to see which values would work on this. And in this case, we see that KSP, hold on a second. So what we're doing is we're actually looking at A first. I should have made that clear because I realized maybe I'm not making that clear. B, we're going to do on the second page. So they picked barium carbonate and magnesium carbonate. Why? Because we want to look at the KSP values. So we need something that would be able to selectively precipitate it out. So barium carbonate is a KSP of 2.58 times 10 to the negative 9. Magnesium carbonate is 6.82 times 10 to the negative 6. So it says right here, barium carbonate is less soluble by several orders of magnitude, because this is a big difference. So we can use that to selectively precipitate using sodium carbonate. Sorry, my dog's gonna bark. So barium carbonate is the one that we want to use for this situation. So let's take it the next one. So in this case, we want to selectively, so again, suppose you have a solution containing barium magnesium ions. Which of these salts could you actively selectively precipitate barium? So in this case, these we compare barium phosphate and magnesium phosphate. In this case, we see that there's a difference of order of 1. So these two KSP values are very close together. So it indicates that if you added sodium phosphate, you would get a precipitate of both ions. You would not get as much magnesium before barium would begin to precipitate out. So, and we don't want that. If you selectively want one, you want a larger different value, KSP value between them, or you're going to pull out both of them. Okay, so in review, in a heterogeneous equilibrium system between ionic solid and a solution, KSP is a measurement of the product of the ion concentration. So what is dissolved? It's on the product side, it's in ionic form. And we also we've taken place with respect to the coefficients. And Q is a measurement of the product of the ion concentrations in any conditions. So we can pick the reaction in any time, and we'll have a different Q, maybe because it's based on how much of the ionic form is in there at that moment. When Q is less than KSP, the solution is not yet saturated. Saturated means it cannot be soluble anymore. Nothing can be added to it. More solid ionic compound will be dissolved. Because it's not saturated, it can take more in. Q equals KSP. That solution is saturated. The system's at equilibrium. And Q is less than KSP. The solution, Q is greater than KSP. The solution is past the point of saturation. It went past equilibrium. And it's the solid ionic compound will be solid form out of the solution until it gets to a value of Q equals KSP. When several ions are present in the solution, one or more ions can be selectively precipitated and removed from the solution based on the different solubilities of ions with specific reactant.